And this is the official start of data mining. So welcome everybody. Today we're going to finish going over, we have one last page of the notes from stochastic gradient descent 2. And then we're going to kind of start a transition period today of start doing less theoretical stuff and more programming stuff. So we'll start today talking about how to use PyTorch to implement stochastic gradient descent. And really the rest of this course, so the next 6 weeks or so, we're going to be really implementation focused. And so previously we were maybe like 80% theory, 20% implementation, and now we're going to reverse that on its head to 80% implementation and programming and 20% theory, sort of connecting the code that we're writing to all of the theorems that we reviewed in the first half of the course. So I think a lot of you will find the second half of the course more easy than the first half. My sense is, or my experience is that most students find programming much more intuitive than math. So that's probably a good thing for you all. And I intentionally structured the course this way with trying to have the programming stuff at the end, since for most courses, the sort of difficulty ramps up and gets more and more difficult as the course progresses. So I wanted to have this sort of easier portion of the course at the end, so that at least in this course, things are maybe ramping down in terms of difficulty for you as your other courses are ramping up. So that's overview of what we're doing today and short preview for the next couple weeks. But I'm going to share my screen now and we'll finish up the notes on the theory portion. Okay, so I have open right now the last problem from the stochastic gradient descent 2 notes. And this one was not actually about stochastic gradient descent. It was about the nearest neighbor algorithms. But the reason it fits in here is because it's related to, or this theorem relies on Lipschitz continuity to provide a bound, generalization bound for the nearest neighbor algorithm. And so I'm just going to highlight some of the key things in this theorem, and then we'll talk about this question down, part 2 down here. Again, like normal, if I say something that doesn't make sense, feel free just to interrupt me and ask clarifying questions. So this is this theorem is about the one nearest neighbor algorithm in particular, and the we talked before about how the VC dimension of one nearest neighbor, the VC dimension of one nearest neighbor was equal to infinity. And that means that nearest neighbor is not path learnable or agnostic path learnable. But there is, if we make some assumptions about the data distribution, then these, the nearest neighbor algorithm can be learnable under those assumptions. And the particular assumption that we're making right here is that the conditional probability function or distribution function is C Lipschitz. So to get some intuition about what that sort of might look like, I'm going to draw a picture down here, which is sort of related to the answer to this number 2 question about what does it even mean for our distribution to be Lipschitz. And so our data space here, I'll just use the real number line to make the pictures easier. And down here, so here, just our x, the real number lines, and then the y value that I'm going to draw is the sort of the probability value. So the probability that y equals either 0 or 1, or we'll do plus or minus 1 to make it a little bit easier notation-wise, plus or minus 1, given x is what's on the y value. And there's a number of possibilities. So we could have, say, like two sort of Gaussian looking curves like this. And I've drawn two curves here, one for the +1 case and one for the -1 case. And now when we're talking about if the distribution itself being Lipschitz continuous, we're talking about these functions actually being Lipschitz continuous. So these are relatively flat distribution functions, but I could have drawn significantly steeper distribution functions that maybe look something like that for +1 and that for -1. So here, the rho value, the Lipschitz constant, is relatively small on the top. So I'll use C since in the theorem they're using C for the Lipschitz. We have a small c up top, and we have a large C down below, down here. And again, that's because you find the location that's sort of the steepest, that has the highest derivative, and that's going to be the value of the Lipschitz constant. And these distributions down here are much steeper than these distributions up here. So these are sort of the pictures to keep in mind about small c and large c. And we're going to go back up to the theorem here for a second to see what that means. So now in this theorem, we're still in the binary classification case. So in the book, they wrote it as 0, 1. It's really the same as plus and minus 1. The actual numbers don't matter. It's just the fact that it's binary that's important. Here, the data space, the key thing to notice here is that the distribution or the dimension of the distribution is D. So down here, when we get these D values, that's our dependence on the distribution right there. And then the C value right here is our dependence on the Lipschitz value. Over here on the left, this is our training error. And then over here on the right, this is our generalization error. And you'll notice a couple peculiar things right here. The first is that we have this 2 value in front of our generalization error. So what this theorem states is that no matter what your Lipschitz constant is, no matter what your dimensionality of your problem is, no matter how many data points you have, we cannot guarantee that nearest neighbor is going to do better than, or that the training error is going to do better than twice the generalization error. And so this means that if your generalization error is large, then, or sorry, if your approximation error is large, this right here is the approximation error. It's the approximation error. If your approximation error is large, then this bound over here is going to be potentially really, really bad, because if our approximation error was 0.5, then 2 times 0.5 is equal to 1. And for any algorithm, the difference between our training error and generalization error is going to be less than 1 on the 0-1 loss. So this tells us that it can only work well when our approximation error is already really, really low, because of this 2 right here. The next thing that this theorem tells us is that as our, and this is sort of like the important part compared to VC dimension, as our Lipschitz constant C here increases, then our bound between our training error and our true error is going to increase as well, proportional to the Lipschitz constant. So that means this situation right here is an example of the more easy data set. And this situation right here is an example of the more hard data set. Intuitively, the reason why this is a more hard data set is because right now I've drawn these distributions of +1s and -1s as sort of unimodal distributions. but they could be very non-unimodal. So I could have a +1 here, -1 here, and then another +1 here, and another -1, and another +1, and another -1. And the fact that I have a large C means that I can squeeze a lot of these changes from +1 to -1 inside of this region right here. Whereas the fact that C is small here guarantees that there's going to be a large region of +1 before I switch to -1. Why that's important is that in my training set, if I just have, say, one point in this region right here, it can kind of cover all of this space with the nearest neighbor, and everything in here will be classified as +1. And then my 1 point over here can cover all of this space, and everything over here will be classified as -1. But down here, if I have just those same 2 points, then it's guaranteed that in that region, there's going to be a lot of +1s and -1s switching back and forth. And guaranteed a lot of +1s and -1s. And so in order to get good, make my training accuracy reflect my true error, I really have to have one data point for each one of these sort of modes of my probability distribution. And in a large C case, that means there's a lot of modes, so I need a lot more data points. How that relates to the VC dimension again is that, so the VC dimension is again a bound for all possible distributions. And this bound right here, we'll see that in the limit as C goes to infinity, these modes become sort of infinitely narrow, and you get a +1, -1, +1, -1 alternating back and forth, infinitely put together. And so it makes sense that that's a really, really hard distribution for nearest neighbor to work on. And so that's the distribution which sort of justifies as the hard case and why we can't be path learnable. But typically, we're not in that sort of really, really weird distribution case. We're in a more smooth distribution case, and this Lipschitz C constant captures that sort of effect. Are there any questions about that?
Yeah, Mike, I know we went through this like a while ago, but just to confirm, can you restate what LDHS and then what LDH star in the context of like a training and a test set?
Sure. So the LDHS, this is the true error of your hypothesis class. So that's the performance on the test set, and LD of H star is so LD again, the true error, H star is the best possible hypothesis in your hypothesis class. So here the HS is the model that you've trained, and the true error of the model that you've trained is guaranteed to be, if we compare that to the best possible model in your hypothesis class, we can't get within a factor of 2 of that best possible model. So both of these LDs mean that it's on the test set. HS means this is the model that we're actually considering. H star means this is the best possible model in your hypothesis class.
Okay, so this is saying that even in the best possible case, we can at most have 2 times the true error as our, basically we can train our model to at most 2 times the true error.
At most 2 times the best possible error.
Yes, sir, the best possible error.
Mm-hmm. So yeah, like we know that the So here, LG of H star is the best possible error in your hypothesis class. We know that this is guaranteed to be bigger than the Bayes error of your particular problem, because the Bayes error is dependent only on the distribution and not on the hypothesis class. And so the true error of your one nearest neighbor model cannot be better than twice the Bayes error of the problem. So for any problem in the like 0, 1 binary classification regime, like the Bayes error at worst is going to be 50%, because that's just like random guessing, that there's the input data has no impact on what we're guessing. And so we're just guessing 0 and 1 randomly, and that your Bayes error is 0.5 in that case. The nearest neighbor algorithm is really, really bad in that situation when the X input vector is uninformative, because we can't guarantee even that you're going to get anything possibly correct. When the Bayes error is really close to 0, though, that's a situation where nearest neighbor can potentially shine. If your Bayes error is really close to 0, then this term right here will go to 0, and you only have to consider this term over here. And so if your Bayes error is 0 and your Lipschitz constant is relatively small, so that the data is sort of smooth like this, not unsmooth like this, then that's the situation where nearest neighbors can potentially be good. Yeah, so in terms of like, what's the thing that you really need to know for practical purposes related to nearest neighbor, the answer is that it seems intuitive, can work well in practice on easy problems where easy is defined as having a low Bayes error and the data is somehow smooth. So whatever like you would intuitively think as easy, that's what these two sort of terms capture. But anytime you get into hard or data situations, then nearest neighbor is going to be guaranteed to perform poorly. Any other questions on this theorem?
Mike, I just sort of have a practical question. Like,
Mhm.
if you have some data, how do you know, like, is there a way to assess how smooth or rough your data looks, and sort of have an idea beforehand whether applying nearest neighbors is a good idea?
Yeah, that's a great question. So the question's like, essentially in practice, how do I know whether the data is somehow like smooth or rough? How do I know if that we're in the easy case or the hard case? And sort of there's a couple of possible answers to that. One is visualizing the data somehow. So actually, say maybe do a principal component analysis of the data, look at it in 2 dimensions, seeing is it just like all over the place or is it relatively simple? Other than principal component analysis, there's a lot of other of these sort of embedding techniques that take high dimensional data and let you visualize it. And another popular one's called T-SNE. We'll look at that one in a couple of weeks. That's sort of the main intuitive way. The sort of in practice though, sort of what people do is you try, say, nearest neighbor compared to logistic regression. And if nearest neighbor is like really, really doing bad, having these bad generalization errors, that tells you that it's not even worth looking at any of the sort of variations of nearest neighbor, because you can't sort of improve this Bayes error factor. Typically too, we'll have some sort of intuition about like whether the Bayes error is really small or large for a problem. So for example, if our goal is to predict like stock market movement, then we just sort of know intuitively that thousands of really smart people are investing billions of dollars to be able to predict stock market movement, and they do horrible jobs on average. So the Bayes error of predicting the stock market is high because it's just an intuitively hard problem. And if you look at economists and how they try to predict the stock market, you'll see that none of them use nearest neighbor techniques. And this is sort of an explanation about why that might be the case, because that problem has a high Bayes error, and so these techniques can't be used. Problems that are relatively simple would be like, let's say you're in a medical sort of field and you've specifically been, so like we're working on COVID mortality prediction, and we're specifically been developing tests that have very strong correlation with whether somebody's going to die of COVID or not die of COVID. Then in that case, because we know these tests are really good, we know that these tests are going to cause the Bayes error of the problem to be really low. And so in that case, we might consider a nearest neighbor approach. But yeah, this is usually like a very problem specific thing, trying to somehow use your knowledge of the domain to determine whether the Bayes error is high or low.
Okay, cool.
Great questions. Any other questions about this theorem?
Yeah, Mike, I had another question. So this is for one nearest neighbor. Is there a reason why we choose one particularly, or is there not a way to generalize it?
Yeah, it's a great question. So yeah, this is right, that this is for one nearest neighbor instead of like the more general K nearest neighbor. It turns out that for, so the book has they don't actually formalize this in a theorem, but they have a discussion about how one nearest neighbor compares to K nearest neighbor. And the rough idea is that this term over here, so the dependence on dimensionality and the dependence on the Lipschitz constant, is the same for one nearest neighbor and K nearest neighbor, no matter what the K value is. This term over here, so your the impact of the Bayes error, essentially, this will get lower if you make K higher. And in particular, if in the limit as K goes to infinity, this 2 approaches 1. So if you have K nearest neighbor where you're looking at millions of data points to determine what your classification rule should be, then your impact of the Bayes error is going to be relatively low. But for sort of computational practical reasons and statistical reasons, that's really rare to do. And in practice, people pretty much always use one nearest neighbor if you're using nearest neighbor. Great questions. So what we're going to do next is transition again into more programming related things. And in particular, we're going to talk a little bit more about PyTorch today, something called automatic derivation, which is used in implementing stochastic gradient descent, makes implementing stochastic gradient descent pretty much almost trivial in PyTorch for any model that you might want to use it for. And then we'll also talk about a tool called TensorBoard for visualizing all of these sorts of graphs that we'll be looking at and analyzing in the remainder of this course. On the course webpage, so I've created this new folder for Stochastic Gradient Descent 3, and you'll see that I've already posted the assignment for what I'm expecting you to do for this week. This assignment is due on Sunday of this week. And as a reminder, these notes are due Wednesday of this week. And we probably won't fully cover everything in that's needed for this assignment today, but definitely by Wednesday, we'll have covered everything that you need for this assignment. The thing to make sure that you do by Wednesday is that you get this TensorBoard library installed. This is sort of an extension to PyTorch for visualizing graphs. So make sure that you're able to get this installed, and that'll make the lecture on Wednesday go a little bit smoother, or you'll be able to follow along with what we're talking about. The book also doesn't talk at all about PyTorch or really anything programming related, but there's this tutorial up here, sort of like an intro to PyTorch tutorial that has all the material that that we're covering today and Wednesday. Okay, so what I'm going to do next is actually do some more live coding with PyTorch and show you a little bit more of the features that we didn't go over at the very beginning of class, talking about PageRank. And so typically when I'm programming in PyTorch, I have 3 terminal windows open. This is just the setup that I like. And over here on the left is where I have my editor that I use for coding. And I personally use Vim. So I just opened up this notes.py file over here. And let's just make it a valid Python file real quick. And then over here in this top right window is where I'm going to run the program. And you can see that it's printing out the results. Everything's working. We'll get down to what I use this window here for in a second, but this is for, will be used for that TensorBoard library that I talked about. And so we talked about before how you can, if you want to get access to this PyTorch library, it's import torch, and then you can create tensors in torch by doing torch.tensor. And then if we print it out, it'll just see that our tensor in this case has 1, 2, 3 inside of it. You notice that the program hung for like 4 or 5 seconds there between this line and this line, and that's because importing PyTorch it's a big library, takes a long time to load. Tensor, again, is a generic name for scalars, matrices, vectors, and then generalized to higher order things. The word tensor refers to all of those. This is a first order tensor, has a shape of, or the dimension of its shape is 1, making it first order, and that is equivalent to being a vector. Typically, when I'm debugging things in PyTorch, rather than printing out the actual tensor values like this, it usually makes more sense to print out the shapes of the tensor values, because that tells me whether it's a matrix or whether it's a vector, what the dimensions of the matrix are, things like that. And so here the shape is list 3. I know it's first order because the list only contains 1 element, and the dimension in the size of this particular dimension is 3. We could create a matrix, so I'll do that down here. Say im equals torch.tensor, and that'll be 1, 2, 3, 3, 4, 5, like this, and print out the shape like that, and we'll see that im has shape 2. Sometimes when I'm running PyTorch, I forget if this came up before in the first part of class, but I get these error messages. These error messages are actually, they don't mean anything. I'm using Python 3.5 on my laptop, and Python 3.5 has a bug in it, actually, which is causing these error messages where at the end of the program, Python crashes in an abnormal way. But you can see right here, im.shape equals 2, 3, comes from this line right here. So this crash happened after the program executed. And then we have 2, 3 right here. That's the actual shape of our matrix right here. So everything that we're talking about so far is just a review of what we did a long time ago now for PyTorch. And there's one last review thing that I want us to look at before looking at new stuff, and that's just remind us, how do we do matrix multiplication? So we have this m and this x. If I want to multiply them, then I can say something like m at x. And we'll run that. In all Python numeric libraries, whether it's PyTorch or NumPy or SciPy or TensorFlow, they all use this @ symbol for matrix multiplication. And so this is the multiplication of m times x. And we know that, whoops, matrix multiplication is not commutative. So if I was doing x times m, x times m instead of m times x, PyTorch will throw us a dimension error. Size mismatch, doing a 1 times 3 times a 2 times 3, so that's not allowed. So it has to be in this order rather than this order. So again, this is all a review of what we talked about before in PyTorch. One of the things that really makes PyTorch special, though, is what's called automatic differentiation. And that's really the purpose of the PyTorch library. Automatic differentiation is, it's a relatively standard technique for computing the derivatives of functions, but it's different than symbolic differentiation and numeric differentiation, which are techniques that that you probably saw at some point in your calculus courses. And we're not in this class going to go over the details of how this automatic differentiation works. We're just going to sort of assume that it's magic, because it pretty much is, and be able to take advantage of it. So in Python, in PyTorch, we can define functions like, we'll say f of x, and then we'll return x squared plus 4 times x plus 2. And this is just a normal function that we can call on any tensor in PyTorch. And so if I do say f of 4, this, and I'll print that out and run this. Oops, it looks like I'm still getting my error message right here on line 16. So I'm going to comment that out and then come down here. And now when we rerun it, it should get down to the end of the program and print out this line. And we get f of 4 equals 34. And so here, this number 4 is just a normal Python integer. But I could also say, actually create, we'll use a for a scalar value, equals torch.tensor of 4. And now we'll do f of a and run that. And whoops, it looks like I accidentally capitalized torch right here. So let's rerun that. And now we have f of 4 equals 34, and f of a equals a tensor that contains 34. Again, this tensor is actually a scalar because it has no dimensions associated with it. It's a 0-order tensor. And if I wanted to calculate the derivative of this particular function right here, it's just a quadratic function. So it would be easy to calculate the derivative of this sort of manually. We know how to do that as, what's it, 2 times x plus 4. And we can use the derivative to solve for where this f function is at its minimum, because the minimum is whenever the derivative is equal to 0. And in this case, for this pair of functions, when x equals, what is it, -2, then the function is minimized. And I can just by inspection in this simple quadratic problem figure that out by plugging in -2 right here. -2 times 2 is -4. -4 plus 4 is equal to 0. So we'll real quickly just verify that by saying f of -2 and print that, and then f of -2.1 and f of -1.9. Whoops. F of -1.9, and that. And hopefully, if I haven't made a mistake, this value will be, I guess actually I'm finding a maximum in this case of, let's see, am I? We have that -2 and then two values really close to -2, but not quite -2. Oh, yes, this is the minimum. I forgot that -2 is smaller than -1.9. So yes, we're calculating, or we've sort of empirically verified that -2 is the minimum. The sort of goal of why we're talking about derivatives right now, though, is to talk about stochastic gradient descent. And so when we're doing something like stochastic gradient descent, we want to find these minimum values automatically, rather than by like inspection like we just did before. And so in stochastic gradient descent or regular gradient descent, we had an update rule where we started with some x value, call it xt equals torch dot lowercase tensor, and we'll start at our position equals to 0, and then our update rule was xt equals xt minus some eta times the derivative at xt, like this. So we have our whatever our position is that we're starting at, and we're moving one step closer to it by taking the derivative and moving along whatever our step size is. For illustration purposes, we'll make our step size for now be 0.1. And so let's, right here, we will print out xt before that iteration and xt after that iteration. Run this, and we can see that start off at 0, then we move to -0.4. We're getting closer to our -2. And so what I'll do is put this in a for loop for I in range 10, repeat this 10 times, and hopefully we start converging to that -2 value. And you can see the longer we run this, the closer we get to that -2 value. Yeah, so this is sort of like the pseudocode for the gradient descent iteration procedure to find the minimum of this function f. Right now, we're using this explicitly provided derivative, this df, in this formula right here. And so right now, we're not doing automatic differentiation. In order to do automatic differentiation in PyTorch, what I'm going to do is I'm going to comment out this function right here, or this line right here, so that we can still see what the code is supposed to look like, what the pseudocode is supposed to look like. And now I'm going to say our result equals f of x sub t, like this. So I just call my function, get rid of the highlighting. I just call my function, store it in a result variable, and then down here I'll say result dot backward. This function right here actually computes all the gradients, So in this case, yeah, calling it a gradient, but it's just a one-dimensional function, so you could call it just a derivative. And this sort of automatically knows that what variables this depends on and magically converts your, computes your gradients for you. And then this line right here will get replaced into x underscore t equals x underscore t minus eta times x underscore t dot grad. This value right here, this is the gradient is equal to df of xt. So write that in pseudocode, df of x underscore t equals x underscore t dot grad. There's one last sort of subtlety to, let's see. Actually, before running this like this, got slightly ahead of myself. Let's comment this out before doing it in a big loop and just look at this xt.grad variable by itself. So we have result equals, we'll do it right here, result equals df of xt and result dot backward and x underscore t dot grad. Let's print that value out, and let's print out df of x underscore t, and we're just going to verify that these two things are in fact the same. Go ahead and run that. Whoops, sorry. One last x underscore t. There we go. X underscore t dot requires grad equals true. Oh, let's see, what am I getting wrong? Element 0 of tensors do not require grad and does not have a grad function. Result equals df of xt, result dot backwards. Results equals f of xt. Let's see, I apologize for this. That's one of the downsides of live coding these things, is that I sometimes type out something stupid. So let me go back to my notes and make sure that I'm
Mike, I don't know if this is correct or not, but you're calling backward on result and then you're printing out xt grad. Does that matter? Do you have to be calling result.grad?
Yeah, so this line is correct because I want the gradient of xt, I think. Well, let me just actually type out word for word what I have in my notes down here rather than improvising. So comment out all of those things. And I have x equals torch dot tensor of 0.0, and then z equals f of x and z dot backward, and then x dot grad, printing that out. New data list. Torch dot tensor lowercase. It's not had a grad function. Z equals f of x, z dot backward, x dot grad dot tensor. I apologize for this. Z equals f of x, x equals torch dot tensor of 0.0. Happening on line 37, happening at this call right here, the dot backward equals f of x. F of x. Well, maybe what we'll do is I will figure out exactly what I'm doing wrong right here later, and I will explain a little bit more about the homework assignment. So in the homework assignment, I've given you a code, this train.py code, and this let's see, it's a potentially helpful comment in the stuff requires grad equals true. There we go. Okay, so x dot grad and df of x. Here is the code that is correctly working now, and I apologize again for the hiccup. Let me start from the beginning and explain what's going on, so that to see, I'll explain both what is, how this is working and why what I was doing before was incorrect and why I was causing that error message. So again, we had this f function that we want to compute the derivative of. And so in order to do that, we're at some particular location. I create a tensor for that variable, and I say x dot requires grad equals true. This tells PyTorch that this is the variable that I want to compute the derivative with respect to. And then I say z equals f of x and z dot backward, which this line right here is the line that actually computes the derivative. It computes the derivative and stores it in this variable x dot grad. So any of these variables that have the requires gradient equals true associated with them, it computes, it adds this dot grade attribute to that tensor, and that's where the actual derivative is going to be stored. So here I'm printing out both this x dot grad and this df value, x dot grad and df. And you can see that x dot grad equals 4, df equals 4. And so this is the derivative of this f function at the location of 0. If I were to change this 0 to say 1, then we will compute the derivative of this f function at 1, which is now happens to be 6 instead of being 4. And we said that the minimum happens at -2. So if that truly is a minimum, the derivative must be 0. So hopefully both of these two things will give us 0. And it does, in fact, give us 0 for both of these values. What I was doing wrong before was I was setting the requires grade variable incorrectly. Down here, when I was doing it, I had a typo where I said requires with 2 E's instead of requires with 1 E. So that typo meant that PyTorch did not know that it was supposed to take the derivative with respect to this gradient. And if you ever try to use, so I'm just going to put that second E right here. If you ever try to get this gradient attribute of a variable that you did not specify requires grad equals true of, that's when you get this error message that says element 0 of tensors does not require grad and does not have a grad function. So it's, depending on your opinion, may not be the most helpful error message, especially in this case where there was a typo in that line right there. Let's see, that was a confusing past 10 minutes. So does anybody have any questions about that or anything that covered so far about PyTorch?
Question.
Mm-hmm.
So I see that we have defined df, which is going to be the derivative of the function. So does the backward function, does the backward, it also does the derivative?
Yeah, so this is a great question. Here I've defined this df function, and that's sort of a totally optional thing to do. And let me real quick comment this function out, and I'll have to comment out this line of code right here. But you can see that the code will still work 100% without me manually defining this derivative function. This backward is able to, sort of what it does is it inspects, it sees that we called this f function right here, inspects the inside of the f function, and is able to sort of automatically figure out what this df function is for us.
Perfect. Thanks.
Yep. So yeah, in this case, I mean, so this is a quadratic function, so this is a relatively easy function to take the derivative of, so I could manually write the derivative df down here. But we can see that there's potentially, like in Python, much more complicated functions like this. So let me try this function, r equals 1 for I in range 2, r times equals 2, and then return r plus 4 times x plus 2. So this function right here is semantically equivalent to this function right here. Semantically equivalent meaning it's going to return the same numbers every time I call it. And the reason it'll return the same numbers is what this for loop is doing is it's computing the times equal 2 times equals x. It's computing x squared into this r variable, but it's using a for loop now to do that. And so this will give us the same result as this function right here. And this backward function is still able to like look inside of for loops and calculate derivatives of for loops, calculate derivatives of recursive function calls, calculate derivatives of really, really complex code, things that we not only would it be really hard to do it by hand, but like probably in your calculus class, you did not review what the rules for calculating the derivative of a for loop are. But this backward function just sort of knows what those rules are and is able to do it. So if we run this, we'll see that we get the same value out. Still knows that the derivative is 0. In this case, we could simplify this function down to being this function, but you could imagine there are many for loops functions, very complicated Python functions that cannot be simplified in any way down to a sort of normal simple function call like this. and PyTorch is still able to calculate the derivatives of these complex functions for you. So that's the main advantage of PyTorch over other, say, like other Python libraries or over something like MATLAB, is that it's automatically able to calculate all of these crazy derivatives for you. Any other questions so far?
Yeah, Mike, two quick questions. One is, if you want to calculate like the multiple derivative, or like, you know, second, third, fourth derivative, is there a shorthand, or do you just write, like you put backward in the for loop?
That's a great question. So PyTorch, it turns out, is really only able to calculate first derivatives and not able to calculate higher order derivatives. It's technically possible to force PyTorch to do higher order derivatives because a second order derivative is just a first order derivative of a different function, but it's never done in practice because of computational reasons. It turns out that second order derivatives are significantly more expensive computationally to compute, and so everything in PyTorch is done only with first order derivatives.
And the second question is there a way to get the actual like df out in like function form if it exists?
This is a great question. The question is like, is it possible to actually say return code of the derivative function? And the answer is no. Maybe the short answer is no. The realistic answer is no. The not technically correct answer, or the technically correct answer though, would be yes with a lot of caveats. But in practice, nobody ever really wants to actually calculate the symbolic form of the derivative, and it's not easy to get it to spit it out. Great questions. Any other questions so far? So again, the key thing, takeaway, the key new concepts that we've introduced are if you want to take the derivative of a function, you first define the function, then you create a tensor, which is the location that you want to take the derivative at, set the requires grad equals to true, make sure that you spell it correctly so that we don't have a debugging disaster. Take another variable, set it equal to the result of the function, call backwards on the result variable, and then the gradient is stored on your x variable right here. In order to take this and, or I guess the reason we care about this is, again, for gradient descent procedures or stochastic gradient descent. And so I will uncomment our stochastic gradient descent code and change this so that it will hopefully work. xt.requires grad equals true. And let's go ahead and run that and we'll see what happens. Let's see, so we're still getting that same error message. xt.grad, xt.requires grad, I did spell it true.
On
Yes?
line 54, it's still misspelled.
Thank you. So we're still misspelled right here. And I think because I put it right here, spelled correctly, that, let's see, it's line 54. So for requires gradient here, when I say 0 instead of 0.0, 0 is an integer. Technically, integer value functions can't have derivatives. So let's change that back to 0.0. rerun that. And now let's see, we're getting an error on line 59. Line 59, this df function, I think we commented that out, so it doesn't exist anymore. We'll rerun that. And now we're getting, it's done. So here, xt equals, that's from this line right here. This xt equals is from this line right here. And now we're getting a new error message, this runtime error saying you can only change requires grad flags of leaf variables. So this is an error message that I was actually trying to get, wanted us to see this error message. And what's happening is that, so anytime you get an error message saying changing something with respect to leaf variables, the problem is that we're sort of taking the gradient of too much. We're taking the gradient, in this case, not just of f of x of t, but also with this formula plugged in to x of t. And when we do the gradient descent, we want to not be taking the gradient of these terms down here. We want to only be taking the gradient of f. And so this line right here says block taking the gradients below this formula right here. And so when we call result.backward, it'll only be these 3 lines that it's actually taking the gradient of. This, yeah, it's potentially confusing, this line right here, both because it's an intrinsically kind of confusing concept and because of the error messages that I had before. But the key takeaway is that because we don't want to have the derivative of our gradient update rules, anytime you're doing a gradient update rule, you always want it inside of this torch.nograd function right here. And so it's converging down to our -2 value. If I were to change this from change the number of iterations to something bigger, we'll see that it gets sort of arbitrarily close to our actual minimum value with enough iterations. Are there any questions about that? Okay, so again, the general pattern is you have a for loop. Put the stuff that you want to take the gradient of right at the top of the for loop. So our variable set requires grad equals to true, calculate the result of our function of x, and then do result.backward. And then anything that is part of our actual gradient update step should be within this no grad container right here, this no grad block. In the
Wait, Professor, sorry, could you go over again what the no grad block does?
Sure. So yeah, the question is, what exactly does this, what's the difference between this and if we did not have that with no grad here? And the answer is that when we call this f function right here of x of t, without this x of t actually depends on a lot of other things. So if the t equals to 10, if we're on our 10th iteration, that this x10 depends on x9, depends on x8, depends on x7, depends on x6, and so on. And so when we do result.backward, it'll take the derivative of this, not just with respect to our most recent xt value, but with respect to all variables that occurred in the past. And in order to prevent that, this torch.nograd sort of prevents that and says this stops the back propagation of the gradient at this point. And so our x10, even though it depends on x9, we're not going to be taking the gradient of x9. The details of how that sort of works is super complicated, and it would take more than a semester to fully explain what's going on in this automatic differentiation code. And so it's sort of, in some sense, the right way to think about it as magic, in that you need your gradient update steps, any code that you're not taking the gradient with respect to inside of Nograd here. We're not ever taking the gradient of this formula right down here, so that's why it's in Nograd. The only things you always want to have is have your variable, set requires grad equal to true, immediately call your function on that variable, and then immediately call the backward function on that result. And if you follow that pattern, then things will work.
Can you explain what line 68 is doing again?
Line 68 right here, this is the formula for gradient descent. So at every iteration, our variable xt, we're going to update it by calculating the derivative. So xt.grad is df xt, the derivative, times our step size, and moving in that direction so that we slowly approach the minimum.
Oh, I see.
Great questions. Any other questions so far? Okay. I just really want to really quickly take a look at this training.py code. There's a lot of stuff in here, but the thing that I want us to focus on right now is that there is a training loop down here. So for t in range of big T, and then it has this step right here where it's going to compute the derivative. So it starts with wt.requires grad equals true. We compute our actual loss value, the thing that we're trying to optimize. In the case of gradient descent, it's our L sub s function at wt plus whatever our regularization term is. And then we do the backwards on it to compute the gradients of wt. And then inside of torch.nograd, there is this right here, this update step. We'll go over that in more detail on Wednesday and how to actually run this code and visualize it. But I think we're close enough to the end of class today that we'll stop here. Again, my recommendation for class on for Wednesday before class, try to get the TensorBoard library installed. So if everything works well, it's just pip3 install TensorBoard like that. But you may have, that may not quite work on your system. And I'll post this notes.py file up to GitHub, and that would be a good thing just to try to run it and make sure that this is also working on your own computer. Let's stop sharing my screen now and stop recording. And so that's the official end of class. I'll stick around for a while to answer any questions that people have, but otherwise I'll see you all on Wednesday.